Welcome to this NPTEL lectures on robotics, basics and advanced concepts. So in the last lecture, we had looked at mathematical preliminaries and an important concept called homogeneous transformation matrices. Okay, so in the mathematical preliminaries, basically we looked at how to represent a rigid body in 3D space. So first important thing which we need to do to represent a rigid body in 3D space is to have a reference coordinate system. We are going to use a right-handed coordinate system. We label these coordinate system as A, B and so on. Each coordinate system is defined by means of three coordinate axes, an x-axis, a y-axis and a z-axis and an origin OA. A rigid body in 3D space has 6 degrees of freedom with respect to another rigid body A. So these 6 degrees of freedom are 3 for a position vector, position of a point on the rigid body, and 3 for orientation. So in a sense, the rigid body B is conceptually identical to a coordinate system B. Okay, at this stage, we are not really interested in the shape and size of the rigid body. The position of a rigid body is one of the important concepts. The position of a rigid body is basically the position of a point of interest on the rigid body with respect to the coordinate system A. We are going to use three Cartesian coordinates px, py, pz. One more way of looking at it is we pick a point on the rigid body, and from the origin of the reference coordinate system we draw a vector AP. A denotes that it is with respect to the A coordinate system, and this is a column vector with three components px, py, pz. Okay, so the orientation of a rigid body can be described in many ways. We looked at a 3x3 rotation matrix. We also looked at an angle and axis form, phi and k, and then we looked at Euler angles. Euler angles are basically three angles, and that is the minimal representation of orientation. And we also looked at what are called as Euler parameters and quaternions. Okay, so the 3x3 rotation matrix had 9 quantities and 6 constraints. The angle axis form has 4 quantities and 1 constraint, whereas the Euler angles are minimal. And I showed you that we can derive algorithms to convert one representation of orientation to another representation. When we had a 4x4 homogeneous transformation matrix, ABT, it represented position and orientation in a compact manner. Okay, so the top 3x3 represented the rotation part, and the last column represent the translation part, and the bottom row is 0, 0, 0, 1. Okay, and I showed you that these properties of AB transpose in some sense relate to the general motion of a rigid body, which is nothing but rotation and translation along a line in 3D space. So it is similar to a screw motion. Okay. So as I said, this is a summary of the last lecture. Now let's look at this lecture. In this lecture, we'll look at the elements of a robot. There are two main elements of a robot, joints and links. So we'll start with elements of a robot. And again, the idea is that we would like to represent joints and links in a mathematical form such that we can do analysis with them later on. Okay, so briefly, introduction to joints. Basically, a joint connects two or more links. Okay, so I have two links or more links in 3D space. I can connect them using joints. A joint imposes constraints on the link it connects. So for example, if you have two rigid bodies in 3D space, if they are free, then they have 6 plus 6 degrees of freedom. So each rigid body is position plus orientation, which is 6, and 2 of them means 12. If I now connect these two rigid bodies using a hinge joint, okay, then the second rigid body can only rotate with respect to the first rigid body. So the total system degrees of freedom are now 7, 6 plus 1. So another way of looking at it is that the hinge joint imposes 5 constraints, okay, or a hinge joint allows only one relative degree of freedom. So the degree of freedom of a joint in 3D space in general can be written as 6 minus m, where m is the number of constraints imposed. In a serial manipulator, all joints are actuated most of the time. Okay, and as a result, only 1 degree of freedom joints are used, because it is sort of difficult to put more than one actuator at one place. To implement a multi-degree of freedom joint, we don't use multi-degree of freedom joints in a serial manipulator. However, in a parallel and hybrid manipulator, some of the joints are passive. We'll see this later as we go along in this course, that we can have passive joints in a parallel manipulator. And since these joints are passive and hence we do not need to put actuators, we can easily use multi-degree of freedom joints. So we'll see later that a parallel manipulator, a spherical joint is used, or even a hook joint is used. Okay, so continuing, what are some of the main types of joints? So symbolically, we have these joints. Screw is denoted by an H, revolute joint by R, prismatic by P, cylindric by C, spherical by S, planar by E, and hook joint by T. Okay, a screw joint has 1 degree of freedom. So what is the 1 degree of freedom? Think of this white portion as one rigid body and the hatched portion as another rigid body. The white portion can rotate about this hatched portion and also translate up. But the rotation and translations are related by the pitch of the screw. Okay. Whereas in a revolute joint, also sometimes called as a rotary joint, these are the two rigid bodies. One is at the center and one along this lines or axis, and symbolically shown as one rod here and another axis here. The rigid body here can rotate with respect to the other rigid body by an angle theta. It cannot translate. Okay. A prismatic joint, on the other hand, the two rigid bodies shown here and here, they can translate with respect to each other, and the variable used is d. So a rotary joint, the typical variable used is theta. In a prismatic joint, typical variable used is d. We can also have a cylindric joint, which is in some sense a generalization of a screw joint, where the theta and d are not related. Okay, they are two independent. A spherical joint has 3 degrees of freedom. A spherical joint is also sometimes called as a ball and socket joint. So basically I have one link here and another link here. The second link can rotate with respect to the first link about 3 different axes. Okay, so it has 3 degrees of freedom. The hook joint is sometimes the symbol used is T, sometimes U, sometimes U. It is 2 degrees of freedom. Okay, so U comes from universal. So basically we have one rigid body connected to this one ring and the other rigid body connected to the second ring, and in between there are these 2 bars which sort of connect each other. And what you can see is this, both of these rigid bodies can have 2 rotations about 2 different axes, one along this and one along this vertical. So hence it is 2 degrees of freedom. So as I said, one of the important thing is a joint imposes constraint when you connect 2 rigid bodies by a joint. So let us look at the constraint imposed by a rotary joint. Okay, so in this figure, what we have is a rigid body I and a rigid body I minus 1. It is connected by a rotary joint. So the rotary joint is represented by an axis or a line along which it rotates. So this is labeled as K, and it can rotate by an angle theta I. The rigid body is, as usual, represented using a coordinate system, xi minus 1, yi minus 1, zi minus 1, if the rigid body is labeled I minus 1. Okay, and there is an origin OI minus 1. The next rigid body, the ith rigid body, also has 3 axes, xi, yi, zi, and an origin OI. The origin of the ith coordinate system can be represented by a vector OI with respect to 0 coordinate system. the origin of the I minus 1th coordinate system or the I minus 1th rigid body can be represented by a vector O I minus 1. Okay. Now let us pick a point on the joint axis. Okay, so I can find out this point from the reference coordinate system, the 0th coordinate system, by a vector 0p. Okay, whereas the same point can be obtained by going from the origin of the reference coordinate system to the origin of the I minus 1th rigid body and a vector I minus 1p. Likewise, I can reach the same point first by going to the origin of the ith rigid body and then a vector from there to that point on the joint axis. Okay, so this is the story. So we want to know what are the 5 constraints which are imposed by this revolute joint when connecting two rigid bodies I minus 1 and I. So first thing that we can see is this rigid body I can rotate about k with respect to I minus 1. Okay, so hence the rotation matrix which describes the orientation of rigid body I can be obtained from the rotation matrix of rigid body I minus 1 by simply pre-multiplying or post-multiplying this is O I minus 1 R with the rotation about k by theta I. Okay, so this relationship is straightforward because the revolute joint allows only one rotation about this k axis. Now this is a matrix equation. However, it's a matrix equation. On both sides of this matrix equation, we have rotation matrices. So there are only 3 independent equations. Okay, rotation matrix has 3 independent parameters, which is what we saw in the first lecture. Theta I in this matrix equation is unknown. Okay, so hence there are only 2 constraints. So if I relate those 3 independent equations, parameters on each side, but one of those equations will contain theta I, which is an unknown. So there are basically 2 constraints in these 3 independent equations. Likewise, this point on the joint axis, as I said, can be reached from O origin of the reference to the origin of the I minus 1 rigid body and then this vector, and likewise this origin of the ith rigid body and this vector, and then both of them must be equal. So this is a vector equation. O of p is O of I minus 1 plus O I Ri I minus 1 p and so on. Okay, why do we need this rotation matrix? Because if you want to add these two vectors O I minus 1 and I minus 1 p, we need to write it in the same coordinate system. So this is a vector equation with 3 constraints. So how many constraints we get? We get 2 constraints from the matrix equation and 3 constraints from the vector equation. So hence we have 5 constraints imposed by this rotary joint. The same story happens when you have a rotary joint in a loop. So for example, if you have a 4-bar mechanism and we have a rotary joint connecting 2 links in that loop, or any other mechanism or a closed loop mechanism with rotary joint. So I can again show you that I can reach this point on the joint axis either by going from a reference coordinate system, in this case the left coordinate system, let's say, and or we can go from LO0I plus I minus 1p. Likewise, I can also reach this point by going from the left fixed coordinate system to the right fixed coordinate system, because in a loop there will be more than one fixed coordinate system, and then we can go from R to ith and then IP. Okay, so from the origin of the ith coordinate system to the point on the joint axis. So we have now 3 constraints which has LOI minus 1 plus I minus 1 IP plus LD plus this is equal to this. Okay, so again we have a vector equation with 3 constraints. Likewise, as in the first case, we have a rotation matrix of this ith rigid body can be related to the rotation matrix of the I minus 1th rigid body by simply post multiplying L I minus 1 R to I minus 1 I R. Okay, again a rotation by k theta. So this is also a matrix equation, but with two constraints because theta I is unknown. So if the rotary joint is in a loop or just connecting two rigid bodies in space, we always get 5 constraint equations. Okay, 5 constraints. So hence the rotary joint has 1 degree of freedom. Let's look at a spherical joint. A spherical joint is also called as a ball and socket joint, allows 3 rotations. Okay, so there must be 3 constraints. Okay, so one way of looking at it, a spherical joint is representing a spherical joint as 3 intersecting rotary joints. Okay, that is one way. The other way is, let's look at it directly as a spherical joint. So I have a rigid body I minus 1 and a rigid body I. So they are connected by a spherical joint. So I can reach the center of the spherical joint or some point on the spherical joint first by going to the origin of the ith coordinate system and then from the origin to the center of the spherical joint. So OI minus 1 plus I minus 1 P must be equal to OI, origin of the ith rigid body, plus this vector IP. Again, we have to pre-multiply properly using rotation matrices so that we can add these two vectors properly. So we will get one constraint equation, which is a vector equation, and there are 3 components, hence there are 3 constraints. Okay. So the spherical joint imposes 3 constraints on the relative degrees of freedom of this ith rigid body with respect to the I minus 1th rigid body. In many parallel robots, we'll come across this SS pair. Okay, what is an SS pair? Basically, we have a rigid body I and we have a rigid body J, and they're connected by one S joint which is connected to the rigid body I, another S joint which is connected to the rigid body J, and in between there is a link. Okay, in between there is another rigid body of length Lij. So this happens very often, so it is worthwhile to see what is the constraint posed or generated by a SS pair. Okay, so the basic idea is the distance between these two spherical joints is constant. Okay, and mathematically what can we say? We can write that this vector which is on one of the spherical joints, which is LSI, and the vector which is the other spherical joint, which is LD plus RSJ. R and SL are the two reference coordinate systems, and the distance between these two is constant. So LSI minus LD plus RSJ, the dot product with itself should be equal to Lij square. So this is a scalar equation, and hence it has one constraint. Okay. So with this, we'll come to a stop about representing a joint and its constraints, but we can find the constraints imposed by other joints if you so desire, if it is really required. Now let's look at the elements of a robot, the second main important element of a robot, which are the links. So as I have mentioned earlier, a link A is a rigid body in 3D space. Okay, so any link is basically a rigid body in 3D space, and it can be represented using a coordinate system A. Okay, so rigid body requires a point on the rigid body and some 3 coordinate axes which describes the orientation of the rigid body, and that is the same as the origin of the coordinate system and the X, Y, and Z axis attached to the coordinate system. So a rigid body in 3D space has 6 degrees of freedom, 3 rotations plus 3 translation. So it must have 6 parameters. Okay, so if you have 2 rigid bodies, as I have mentioned, okay, so you need 6 parameters to represent one rigid body with respect to the reference coordinate system or with respect to another rigid body. If the 2 rigid bodies are connected by rotary or prismatic joint, okay, it is possible to use 4 parameters. Okay, and these were invented by Dennewitt and Hartenberg in 1955. Okay, these are the very well-known DH parameters, 4 parameters of a link. The important thing to remember is this is not two generic rigid bodies in 3D space. These are two rigid bodies connected by either a rotary or a prismatic joint. So these four parameters are related because to rotary and prismatic joint, because we will see later that we are looking at joint axis. We are looking at lines in 3D space. Okay. And those of you who know studied a little bit about lines in 3D space, a line in 3D space is referred or represented by four parameters. Okay. Nevertheless, let's not worry about lines and points in 3D space. We'll look at these DH parameters now. For multi-degree of freedom joints, we cannot use these DH parameters directly. One way of using DH parameters is to make use of equivalent number of 1 degree of freedom joints. So for example, a spherical joint, which is the 3 degree of freedom joint, can be represented by 3 intersecting rotary joints, and hence we can again use DH parameters for the rotary joints. So we continue with Delawitt-Hartenberg parameters for a link. A word about the conventions. There are several ways to derive the DH parameters. Okay, initially there were many people who derived their own DH parameters. Nowadays there are not that many ways DH parameter conventions. However, there is still a few. So we will use the convention in the following way. Okay, so in our convention, the coordinate system I is attached to link I. Okay, the origin of I lies on the joint axis I, and the link I is after the joint. Okay, so in a serial robot, after makes sense because we have numbers increasing from a fixed reference coordinate system, which is 0, link 1 has a label 1, and so on, all the way to the free end, which has a label n. Okay, in a parallel robot, this notion of after is not so straightforward. Okay, because there are several loops, so I can go to one particular link by more than one ways, in more than one loop. So it is not very clear what is after. Nevertheless, we will stick to this notion of after. So the joint axis is labeled I, and the link I is after the joint I. Okay, this is the same convention that has been used in Craig as well as in Portal 2006. So let's look at 3 intermediate links which are labeled as I-1, I, and I+1. So we want to assign coordinate axis to these links. So this is very useful and very important. This is one of the most important part of the DH convention. How do we find various dimensions from such a drawing or such a figure? So we have 3 rotary joint axes. These are labeled Zi-1, Zi, and Zi+1. So this is one rotary joint axis, which is Zi-1. The next rotary joint is Zi, and the last rotary joint is Zi+1. So as I have said, the link I-1 is after the joint axis Zi-1. Link I is after the joint axis Zi, and link I+1 is after the joint axis Zi+1. Okay, so in this figure, we look at several things which are useful. Okay, quantities. First is between this Zi-1 and Zi, there is a twist, there is an angle which is denoted by alpha I-1. So how do I find this angle? We project these Zi axis onto here. Then we have a line which is mutually perpendicular to Zi-1 and Zi, that is labeled as Xi-1. So we find the angle between Zi-1 to Zi about axis Xi-1. Okay, so this angle is alpha I-1 as shown here in this figure. Then the distance between the foot of this common perpendicular between Zi-1 and Zi, okay, that distance is AI-1. And this foot of this common perpendicular intersects this joint axis at some point. That is the origin of the I-1 coordinate system. Okay, so there are these lines which is along the zi minus 1 joint or zi minus 1 direction, and then there is another line li along the ith joint axis, and we can always find a common perpendicular between li minus 1 and li, and that is the direction of xi minus 1. So we have zi minus 1, xi minus 1, and the origin fixed. Y-axis is common, is following the right-hand rule. So y-axis will be somewhere here, which makes x cross y as z. Likewise, for link I, we have a common perpendicular, which is this some dotted line here, which is not really shown. Okay, so sorry, this solid line here. And then we have this origin of the ith coordinate system at the foot of the common perpendicular. So this is OI. The x-axis is along this solid line. So this is xi. Xi is not being shown here very clearly. So again, we have a coordinate system which is xi, zi, and again yi will form the right-handed coordinate system. So for every link, say for example link I have a coordinate system labeled I. For link I minus 1, I have a coordinate system labeled I minus 1. Okay, so between these x-axis xi minus 1 and the next, which is that xi, the distance is called di. Okay, so this is the link offset. Likewise, if I project this xi minus 1 to this dotted line here, then the angle between these two lines is called theta I. So we have the assignment of axis, which are the z-axis is along the joint axis, the x-axis is along the common perpendicular, the origin of the coordinate system is on the joint axis, and so on. Okay. So as I was saying, for coordinate system I minus 1, zi minus 1 is along the joint axis I minus 1. Xi minus 1 is chosen along the common perpendicular between lines Li minus 1 and Li. Yi minus 1 is z cross x, which form the right-handed coordinate system. The origin OI minus 1 is a point of intersection of the mutual perpendicular line and line Li minus 1. So origin OI minus 1 is on the joint axis along Zi minus 1. Likewise, for coordinate system I, Zi is along the joint axis I, Xi is along the common perpendicular between Zi and Zi plus 1, and the origin of I, which is OI, is the point of intersection of the line along Xi and line along Zi. Okay. Okay. Again, to recapitulate, we have defined as something called as a twist angle. So twist angle for link I has a subscript I minus 1. Okay, this is a result of the convention. Although we are talking about the DH parameters for link I, and one is called twist angle, it has a subscript I minus 1. We have to live with this in this convention. So the angle between joint axis I minus 1 and I measured about xi minus 1 using the right hand rule is the twist angle alpha I minus 1. So it's a signed quantity between 0 and plus minus pi radians. Then we have the link length. Okay, again it's the link length for link I, but with a subscript I minus 1. Okay, so we need to get used to this. So it is nothing but the distance between joint axis I minus 1 and I measured along xi minus 1. And it's always a positive quantity because it's a length. Okay. Link offset di, this is measured along zi from xi minus 1 to xi. So hence, depending on where these common perpendiculars are intersecting the joint axis, it can be either plus or minus. Okay. Or 0 also, if it is parallel. So the joint axis I, if it is rotary, then di is constant. if the joint I is prismatic, di is the joint variable. Okay. Rotation angle theta I. Okay, this is the angle between xi minus 1 and xi measured about zi using right hand rule between 0 and plus minus pi radians. Okay, so joint I is prismatic, theta I is constant. If joint I is rotary, theta I is the joint variable. So now let's look at some special cases. Okay, the first special case, there are 4 of them. The first special case is if the consecutive joint axes are parallel. Okay, if there are 2 lines in space which are parallel, then there are infinitely many common perpendiculars. Okay, so if you have 2 joint axes which are parallel, then the twist angle or alpha I minus 1 is 0 or pi. Okay, and ai minus 1 is same for all the common perpendiculars. So you pick any of them. Okay, so ai is along any common perpendicular. If the joint I is rotary, di is taken as constant, often 0. Okay, if joint I is prismatic, theta I is taken as 0. Okay, so if 2 consecutive joint axes are parallel and that joint axis is rotary, di is taken as constant. You cannot have 2 consecutive prismatic joints. Okay, so prismatic joint allows basically slide translation along the joint axis. So if we have 2 prismatic joints and they are parallel, then the third rigid body after the 2 consecutive joints will be, we cannot distinguish between the motion of these 2 prismatic joints. Okay, so it will be both, it doesn't matter. So 2 parallel prismatic joints is basically equivalent to 1. If you have consecutive joint axes which are intersecting, this is another special case. ai minus 1 is 0 and the x-axis is normal to the plane. Okay. That is obvious, right? If you have 2 lines which are intersecting, they determine a plane, and the ai minus 1 is the distance between the 2 joint axes, which in this case is 0. The other special case is for the first link. Why is it a special case? Because we do not know z0 and hence x0 is arbitrary. Remember, x0 is required to find the ai minus 1. Okay, so ai minus 1 is the distance between x0 along x0 between z0 and z1. Okay, so since there is arbitrariness in choosing z0, x0 is also arbitrary. So we have a convention which says that the rotary joint, we choose 0 and 1 coincident. Okay, which basically means alpha I minus 1, ai minus 1 is 0 and di is 0. For prismatic joint, choose 0 and I parallel. So which basically means alpha I minus 1, ai minus 1 and theta I are 0. The last special case is the last link. Okay, the last link is special because there is no zn minus 1. Okay, so we cannot find a common perpendicular between, say, let's say z6 and the next one. There is no z7. So in order to resolve this problem, if the last joint is rotary, then the origins of n and n plus 1 are chosen coincident. dn is 0 and theta n is 0. So there is no problem of ai minus 1 and alpha I minus 1 because the z5 is known. Okay, assuming z6 is the last joint. And we choose xn minus 1 to align with xn when theta n is 0. So basically this forms a reference of what is theta n. How do we measure theta n? If the last joint is prismatic, then xn is chosen such that theta n is 0 and origin on is chosen at the intersection of xn minus 1 and zn when dn is 0. So this is another way of specifying what is the 0 position of the last prismatic joint. Okay, so we now have these 4 dh parameters. Okay, alpha I minus 1, ai minus 1, di and theta I. So what do we do with them? So one obvious thing is to represent the position and orientation of the ith link with respect to the I-1th link. Okay, so what is the orientation of link I with respect to I-1? We'll go back to the figure, but let's just write mathematically first. So what you can see is the rotation matrix is nothing but a rotation about x-axis by alpha I-1, and then a rotation about z-axis by theta I. Okay, and the location of the origin of ith coordinate system is first go along x-axis by ai minus 1 and then go along z-axis by di. Okay, we have to make sure that all the vectors are written in the same coordinate system. So let's quickly go back and see the picture to convince ourselves. So this is the link I, this is link I minus 1. How do I go from the origin of link I minus 1 to the origin of link I? I have to go along xi minus 1 by ai minus 1 and then di by zi. So this vector, this plus this. How about rotation or the orientation of link I with respect to link I minus 1? There are two angles. Okay, remember alpha I minus 1 and theta I. So first I have to rotate, I make a simple rotation about x-axis by alpha I minus 1. Then I have to make another simple rotations of theta by angle theta I about z-axis. Okay, so these are the two rotations which are happening, and these are the two translations which are happening. These are the 4 DH parameters basically. Okay, let's go back to the equation once more. So I minus 1 IR is nothing but simple rotation about x-axis by alpha I minus 1 followed by a rotation of theta I about z-axis, and the location of the origin I minus with respect to I minus 1 coordinate system is this. Okay, ai minus 1 along xi and di minus 1 along zi. So we recall that this I minus 1 xi is 1, 0, 0. How about I minus 1 zi? Where can we get this from? This is nothing but the last column of this rotation matrix, I minus 1 IR. Okay, remember that the rotation matrix of a coordinate system B with respect to A, the first column is the XB with respect to A, second column is YB with respect to A, third column is ZB with respect to A. So here we have ZI with respect to I minus 1, which will be the third column of this product. Okay, and it turns out that this is given by 0 minus S alpha I minus 1, C alpha I minus 1. Okay, so what is alpha S alpha I minus 1? It is sine alpha I minus 1 and cosine alpha I minus 1. Okay, so now we can assemble the 4x4 homogeneous transformation matrix which relates coordinate system I with respect to I minus 1 or describes link I with respect to link I minus 1. So as usual, there is a top 3x3 rotation matrix. Where is the rotation matrix coming from? From this equation, product of rotation about x and product with followed by a rotation about z. So you can see that you will get c theta I minus s theta I 0 and various sine and cosine theta and sine alpha. The last column is the translation, which is ai into 1, 0, 0 plus di into 0 minus s alpha I c alpha I. So we'll get this, and the last row is 0001. Okay, so as you can see that I can describe link I with respect to link I minus 1 using these 4 DH parameters. What are those 4 DH parameters? Just to recapitulate, theta I, ai minus 1, di and alpha I minus 1. 2 angles and 2 distances. The important thing to note is that this 4x4 homogeneous transformation matrix is function of only one joint variable, either di or theta I. So if the joint axis I is rotary, then theta is the variable. If the joint axis I is prismatic, then di is the variable. All others are constant. Okay, why? Because again, remember we are dealing with 1 degree of freedom joints. So actually there should be only one variable, which is the joint rotation or the joint translation. This vector I minus 1 OI locates a point on the joint axis at the beginning of the link I. That is important. Okay, so the origin is always on the joint axis and the link is after the joint axis. Okay, so it is at the beginning of the link. So it does not capture the length of the link after the joint. Okay, that is what I'm trying to say here. Position and orientation of link I is determined by alpha I minus 1 and AI minus 1. Okay, so this is the confusing part of the convention. We are talking about position and orientation of link I. However, the symbols it contains are alpha I minus 1 and AI minus 1. Okay, so is this very serious? If you think about it, it is no, because whenever we are talking about position and orientation of link I, it is always with respect to link I minus 1. So this carries that information. Alpha I minus 1 and AI minus 1 refer to what is happening to the previous link. So the mix of these subscripts are a convention of DH convention which is being used. Okay, you cannot avoid it. There are other kinematicians who have developed their own version of DH convention. In all of them, some problem like this always happens. So in some others, it is I and I plus 1. Okay, now if I want to find link I with respect to some other reference coordinate system, let's say 0, okay, all I need to do is multiply all these transformation matrices, okay, just by the rule of matrix multiplication. So O to I is nothing but O1, 1, 2, I minus 1, I. Okay, we can also obtain the position and orientation of any link with respect to any other link. Okay, so if I want to find, let's say, fifth link, I equals 5 with respect to 2, second link. So 2 5t is nothing but 2 3t into 3 4t into 3 4t and into 4 5t. Okay, so it is always possible to obtain position and orientation of any link with respect to any other link by just suitably multiplying relevant 4 by 4 transformation matrices. So in summary, we have two main mechanical elements of a robot. These are links and joints. The joints allow relative motion between the connected links. Another way of saying joints impose constraints. A serial robot or a serial manipulator mainly uses 1 degree of freedom rotary and prismatic actuated joints. However, in parallel and hybrid robots, we can use passive multi-degree of freedom joints and actuated 1 degree of freedom joints. We cannot use multi-degree of freedom joints in serial robot because it is difficult to put 3 actuators. Let's say we want a 3 degree of freedom joint somewhere. 1 degree of freedom rotary and prismatic joints are represented by lines along joint axis, and we always label the z-axis along the joint axis. Okay, we choose or label the joint axis as z-axis. The formulation of constraint imposed by several kinds of joints was discussed. So for example, the rotary joint imposes 5 constraints. So I showed you there is a rotation matrix equation which imposes 2 constraints, and then there is a position based vector equation which imposes 3 constraints. A link is a rigid body in 3D space. It is represented by 4 Denavit-Hartenbach parameters. So basically they are alpha I minus 1, AI minus 1, theta I and di. There are 2 lengths and 2 angles. And I showed you that there is a convention to derive the DH parameters, and then there are special cases in the DH parameters. With these DH parameters, we can go ahead and determine this 4 by 4 link transformation matrices in terms of the DH parameters. So basically this 4x4 homogeneous transformation matrices contain all the information about the position and orientation of one link with respect to the previous link. So with this, we'll stop in this lecture. In the next lecture, we will look at examples of DH parameters and examples of link transformation matrices for different commonly available robots. Okay, thank you.